Tertiary carbonide is at least stable, okay? Clear is the opposite of carbonide. And the reason for this is because the methyl is what? Electron withdrawing or electron releasing? We are going to go back as if we were in what class? We did this last class. I remember. Yes or no? Yes?
Yes.
So all of them are pushing down. So overall, it will release electron density. So here's electrons, and if you give it more electron density, what is that going to do to this? Stabilize or destabilize? It's going to destabilize it. It doesn't like more electrons. They want something that is going to withdraw electron density, so it has electrons, it stabilizes this charge by adding to it. So how stable is this right here? Not stable at all. It doesn't like it this way. It doesn't want it. If you would have added this, so let's say you would have added this, let's say we added it to this side. Let's say we added it to this side, and it goes like this. One from there. Say it goes like this, right? It goes here, that goes there, this one goes here. Now this electron goes here, that there, it's here. Which one is more stable? Is this more stable or is this more stable?
The one on the bottom.
This one is more stable. Because this is more stable, this is what happens. And then an electron now. A hydrogen or a proton gets pulled off from this alcohol. We did this mechanism, didn't we?
Yes.
A proton gets pulled off from that alcohol, and then another sodium donates it to this. A negative charge here, and then overall, this will end up with this structure, in which the methyl group, whatever they said, the methyl group goes on the double bond. Okay?
Professor, they actually had a problem like that. Question 8.25 in the newer book, and it was with anisole. And it was saying how anisole actually can act as electron donating and releasing, but it will be more so donating because of resonance, because it predominates over inductive effect.
Because if you have an oxygen on one of the sides, the oxygen, and we're not there yet when we do electrophilic, oxygen can, when you have this oxygen here, with whatever, this oxygen can be electron donating by resonance, meaning by resonance, I can make this double bond here, so it gives the electrons to this.
Right.
But it is also what? It is more electronegative than this, yes?
Mm-hmm.
So it is electron withdrawing as well.
Okay.
Okay? So don't worry about that for the Birch, okay?
All right.
For the Birch, we care about this methyl group, and that's a mechanism for that, which is going to be on the test. I am not going to lie to you. I don't know if you have noticed how many of these mechanisms I have done. So now I want you to do the same with this group. Let's say this is CH3, doesn't matter. Just do the mechanism for it, okay? You guys did it? So it can't take so long, okay? Remember, the test that is coming, people that took my last class, organic one last semester, the test, is the test short?
No.
Does the test have everything?
Yes.
I don't want, for those of you that haven't taken the class, I don't want you to misunderstand things. You are going to have everything I give you, okay? You're not gonna have time to finish the test either. So you better know everything very well, like scary well. Like you can teach it to everybody else, okay? I don't wanna, you get confused. Okay, let's say the mechanism, yes?
Mm-hmm.
Let's do a short mechanism, how about that? Okay, the electron gets donated, we have two choices. It either gets donated here or either here or here.
Yeah. Mm-hmm.
Okay? Wherever it gets donated, it doesn't really make a difference, okay? What matters is that at the end of the day, you are going to have something that looks like this. One in which you're gonna have this here. Yes?
Mm-hmm.
And one in which I didn't do the whole thing. You are responsible for the whole thing. And one in which you are going to have, where's the other one? Where can I put it now?
On the other
On the side. It
Yeah.
doesn't matter if I put it on this side. Doesn't matter if I put it on the other side. And where will be the where the double bonds would be at? They would be
Right
either
there
here,
and right, yeah.
yes,
Uh-huh.
and here.
So opposite each other.
Very good.
Yeah.
Now, question would be, which one is now more
What's
stable?
the one to the right, right?
The one to the right is more stable.
Yeah.
No,
No?
no.
Why?
Why is it more stable? It is more stable
it's not
if it were a
tertiary.
methyl group.
Oh.
But it's not more stable because this is not a methyl group. This is electron what?
Withdrawing.
And this is what
Okay.
happens when you have electron withdrawn.
Damn.
This is a minus charge, yes?
Yeah.
This is what happens.
Because
That-
resonance. Yeah,
and that.
resonance. Okay.
So what you ended up doing here was the negative charge was stabilized.
Ah.
A negative
Went from the
charge now
carbon to
has
the more
a resonance
electronegative.
structure.
Yeah, yeah.
Okay? And the resonance structure stabilizes it. So because this is electron withdrawing, it stabilizes a negative charge on that same carbon.
Mhm.
If it would have been something else, this is positive or negative?
Partially positive.
Positive, and this is negative.
Negative.
That's a good thing. Okay? So some stabilization can happen because of resonance. Some stabilization can happen because of inductive effect. Okay?
Mhm.
If it would have been electron withdrawing and it was not resonance stabilized, it could be an electron withdrawing element here, like a carbon with 3 fluorines, okay, or an NO2. An NO2 is resonance as well. It would be still stabilized because this is a good thing if it's negative here and that's positive. But in the previous one, this was negative, that is also negative. Hello? You want one like that on the test?
Of course.
this is how the question for this would look at like on the test. It would look like, show why you get this product instead of this product from the Birch reduction. Explain this with a mechanism. In fact, show two mechanisms. Okay? This is one of them, yes? Look here. This is one. This is the other. If I ask you, show the intermediates, then you draw these. These are the intermediates, yes? This is not the mechanism. These are intermediates. The mechanism is that. I didn't want to go through the whole thing. We got more mechanisms to do. So, 100% guaranteed you're going to have the Birch reduction mechanism on the test. 100% guaranteed you're going to have electrophilic aromatic substitution mechanism on the test. You know the two you're going to have so far, yes?
Yes.
No tricks. Where's Karen?
She's not here today.
Why not? What happened to her?
FIU
Why are you yelling? Girls, man, I gotta tell you.
Unstable.
I gotta tell you 3 times. All right. So, we were doing electrophilic aromatic substitution, yes?
Yep.
Electrophilic aromatic substitution, you always have what that gets attacked? What gets attacked? Aromatic system does not get attacked. What's wrong with you? The double bond attacks, yeah. What gets attacked?
The nucleophile.
The electrophile.
Yeah.
And the electrophile is made by what? It's made by a Lewis acid or
Lewis base.
a regular acid with something else, okay? That something else can be a halogen. So here is the mechanism for making Br plus. That is the electrophile.
Promoting.
So we have Br with Br. What are the conditions for electrophilic aromatic bromination? What are the conditions?
You mean what is it sitting in? What solvent?
Now what solvent, what do you need to
You
make?
mean a Lewis acid?
Lewis acid? Yes.
FeBr3?
FeBr3 or AlCl3, okay? Or Br3. Okay. Every book that you will ever read has this one. That book, I don't want to say the name, okay? That book that I'm reading has Al. Whatever, it doesn't matter. So this is what happens. This is a Lewis acid. It means it is electron what? Huh? Electron acceptor. Okay, all right. Electron acceptor is electron what? Deficient or electron donate? Deficient, right? It needs electrons. So what's going to happen? Who's going to give electrons to it?
The bromine.
Yeah. Anything that has electrons, we'll give it to the iron. Okay? So what's going to happen is that is going to go that way. Whoops. It's kind of radical. That is going to go that way. And what you are going to form is this. Let's say it's not, okay, whatever. Let's not do it like that. Okay? And now it's going to have a Br with another Br. Do formal charges for this. Okay, this one here is going to be positive.
Positive.
This one is going to be negative. Okay, that's going to, everybody else is neutral. Okay? If you don't know why, don't worry about it, okay? That class already passed. Miss it on the test. Okay, so now what I'm gonna show you next is not what really happens, okay? That's not what really happens, but I gotta show you the source of this bromine plus, okay? And the source of the bromine plus is this here is going to leave, and that is going to keep the electrons, okay? If these electrons from here stay on that bromine, this bromine will become what type of charge?
Negative.
Neutral.
If this bromine takes, it's not gonna be negative, it's positive now. If this bromine, let's say, takes the electron pair, and of course that breaks, what you are going to have is no electrons from here. This is what you are going to have, yes or no? And this is going to be a positive, okay? And this is the source of Br plus. Now that's not what really happens. This does not form. The Br plus does not form. What happens is that this is what gets attacked, okay? And when this gets attacked, that leaves. So if some electrons from somewhere, or a double bond from somewhere, would attack this, then that will take the electrons, okay? So when this is making a new bond, that bond is breaking to form something that is neutral here, and then this is the source of Br plus. Yes or no? I am going to ask you on the test to give me how you form this Br plus or this Cl plus.
In the lab manual, from the lab that we just did about this, it was with nitration, so it was with an nitronium ion. But it said that it could undergo two different reactions. Either it could do like a substitution to form a nitronium ion or an auto-ionization, depending on how much concentration of the ion is needed. Why does that happen? Or would that, if it just broke off by itself, the bromonium, would that be auto-ionization? Why doesn't it do that?
It doesn't do it here because Br plus is not stable. Br doesn't want to be Br plus, but that's how it reacts as Br plus because it gets attacked. But you want to do the other one, yes? You want to do nitration? Now you guys remember, she is provoking me, okay? I wasn't planning on doing it, but she provoked me. So she wants to do nitration. Let me know whatever else you want to do, okay? So nitration, what do you need?
HNO3.
And
Acid.
H2SO4. It is two acids, yes? Two nasty ones. So, do you know how the HNO3 looks like? How does HNO3 look like?
Nitrogen bonded.
Another oxygen and another oxygen. What else?
An oxygen.
This oxygen here, what about this oxygen?
Has a negative.
Has a negative charge?
Yeah.
And this nitrogen?
Positive.
Positive charge, yeah, it has 4 bonds. You do the finger test, okay? People new to me don't know about the finger test. I'm not gonna show you. Okay. So, there it is. And of course, by resonance, this goes this way and that way and blah, blah, blah. So what happens when you have an acid, strong acid, like H2SO4, it gives H plus,
Yeah, two.
and this is going to get protonated, yes or no? It gets protonated, so what happens is, you are going to have this stuff. Okay, this is going back and forth by resonance, okay? And the product only happens if you have this resonance structure, okay? It could go here, the hydrogen as well, but it gets protonated again, whatever it is. It will end up being this 2 hydrogens here. It had 1, second one gets donated to it, and now this becomes positively charged. Because this alcohol is protonated, now this becomes a what?
A good living.
A good leaving group, and the leaving group here is called
Water.
H2O, water.
Water.
So this is a good leaving group, and good leaving groups do what?
Leave.
Like good boyfriends, yes? That's what good boyfriends do. They leave. Leave the girl alone. So, this doesn't have 2 electron pairs here, right?
No.
You erase that, okay? It doesn't have 2 electron pairs. Whoever sees that is going to say, this guy doesn't know anything. I don't. So there you go. The water leaves, and when the water leaves, now this becomes what?
It becomes neutral. The
It
N.
becomes weak.
Excuse me? It took that, and now the electron pairs from here goes like that, makes a double bond there, and what you have is that structure. And this structure has a
Plus.
plus right there. And this is the source of,
Electrophilic.
that is the electrophile. Okay? Now, what they call that, if they call it autoionization or not, is besides the point, okay? All I care about is that you know that what is the electrophile is this thing.
Okay.
And that is how you make it.
Wow.
I have explained to you source of electrophile Br plus,
Yeah.
and I've shown you Br electrophile NO2 plus.
Yeah.
And so in this case, we had sulfuric acid to help it. But in the bromonium case, what acid is we used?
What do you mean?
Well, we have that Lewis acid.
Yeah.
So that's it?
Yeah,
With the two BRs? BR,
Uh-huh.
BR? Okay.
and Br is not a Lewis acid.
No.
FeBr.
The BR, and then the Lewis acid.
Yeah.
Okay.
So we discussed last class, they all have some type of acid, yes?
Right.
This is what type of acid? Lewis, yes, Lewis. Lewis acid, and here is another acid, okay? It's not per se only Lewis acid, but it does fall under the definition of a Lewis acid anyway. Yes? So they're all Lewis acids, but this one is not only a Lewis acid, this is also what type of acid? Bronsted-Lary,
Bronsted-Lary,
and it is
yeah.
also an Arrhenius acid. This is all types of acids. What else? Sophia, anything else?
Yeah, why in this case we need the what is it, nitric acid?
You need an NO2 plus, yes? That's why you have nitric acid.
Okay, so why in the other one we just have BR together? Is that
Because you need Br plus.
But what type of solution is that? Is it just
You mean to say, what is a solvent?
that's what it is? I don't know.
No, the solvent is not B. Those are the
What is
reactants.
the source of the BR?
Bromine gas.
Okay, so
Like
you-
oxygen exists, like Br2 exists.
Okay.
Luis La Vista is spreading it, man, you know? What's wrong with you, man? Okay, guys, so that attacks it. In the other one, SO3 looks like this, yes? Does SO3 look like this? SO3 looks like that, and it is with what else?
Acid.
There is an acid in there too, and this SO3, this sulfur is the one that gets attacked, okay? It doesn't have, it's very positive because it's oxygen and that oxygen and that oxygen taking electron density from it.
Right.
If you were a guy and you had 3 girlfriends, you'd feel this, what the sulfur feels, okay? Completely withdrawn, drained, whatever it is, no money, everything broke.
Even with one.
I mean, one girl does that to you, imagine 3. All right, no, we can make you happy, okay? That's the whole purpose of life. So, that's that. And if you have this one, yes, is the one for what?
Friedel, whatever.
Alfredo, you said?
Friedel-Crafts.
Okay, why don't we do them all?
Yeah,
You want to do them all? Let's do them all. Right, Sophia?
that's all.
I mean, that'll make Sophia happy. That's all we want, make her happy. Okay, and what are we going to have here? We're going to have a Lewis acid. This Lewis acid is slightly more violent than that one, okay? This Lewis acid is a bad boy, okay? So basically what's going to happen is Electrons, you see them? Electrons here, just like in the Br2 over there. And what is that going to do? It is
Leave.
going to make a bond
bond,
to this,
okay.
yes?
Yeah.
And make a bond to that. So imagine, bond to this, bond to that. And now what is going to happen next is, this is going to act like the leaving group.
Uh-huh.
What is that going to do?
Leave.
It is going to leave once it's on the aluminum, yes? And now, this is going to become this type of stuff. Positively charged there, with whatever else it has. This is resonance stabilized.
Yeah.
This electron pair goes here to make whatever I showed you before. Yes?
Oh, okay,
To
okay,
make this
okay.
stuff.
Triple bond. Like that.
With a plus here. At the end of the day, it gets attacked here. The one I want you to know is this one. Okay? Now the benzene ring or the double bond from the benzene ring attacks this electrophile. And then what happens here? Once
That
again,
one,
chlorine
chlorine,
is attached to that.
It's
And
gonna
then this
leave,
leaves.
right?
Now
Yeah.
this, we have a problem now, yes? We have a problem in
Primary.
which the carbocation
Is
is
primary.
going to beat that.
Yeah.
Carbocation. Does that want to form easily? Hello? That does not want to
No.
form because this carbocation is
Primary.
primary.
Yeah.
So, when you are doing electrophilic aromatic substitution with, what are they called when you have an alkyl halide? Huh? What is the electrophilic aromatic substitution called when you have an alkyl halide? Friedel-Crafts
Friedel-Crafts.
alkylation. It's not acylation because this is an acyl chloride, this is an alkyl chloride. So acyl chloride, Friedel-Crafts acylation, Friedel-Crafts alkylation. So in the Friedel-Crafts alkylation, the ones that are preferred are those that are either secondary or tertiary.
Tertiary.
Problem with those is they undergo rearrangements. So on the test, I'm not going to ask you, oh, does it rearrange, does it not rearrange? So if I give you something like this on the test, which is better, a Friedel-Crafts alkylation?
The first one.
Okay, this one is better, a Friedel-Crafts alkylation than this.
Right.
Okay, not that this doesn't happen, but this one is better because this carbocation formed from here will be
Secondary.
while this one will be
Primary.
Okay? All right, that's the end of that. And then we do ortho pair. We did ortho pair, yes? And what else did we do? Hello? Sophia, what else did we do?
The last thing that we did was Friedel-Crafts installation.
Excuse me?
The last thing we did last class?
No, I don't know what last thing we did last class. It doesn't matter. What else did we do? We did ortho pair.
Yeah.
We did electron withdrawing and electron releasing groups.
Yeah,
Mm-hmm.
yeah.
We did ortho pair, yes?
Yes.
So let's say we have this here.
We did the
Benzene ring. Okay? There is a benzene ring. What's the product? What?
The NO2 is going to be on the.
I know two's gonna be.
Okay, so these are conditions for nitration. And the conditions for nitration, we'll put a what on the ring? NO2. So there it is. You can put it wherever you want. You can put it here, you can put it here, you can put it here, wherever you want. It doesn't really matter because it's the first one, right?
Okay.
There you go. You like that? Okay, well, if I were a bicycle, what would happen? People be riding me all over the city. Unfortunately, I'm not a bicycle. So nobody be riding me.
Oh, man.
You should have been an organic one, okay? You weren't there, so you don't know the bicycle. So let's say you have this, which is called fuming sulfuric acid, right? What would that give you? This is conditions for sulfonation, and what it gives you is
SO3.
SO3H. Yes? And a benzene ring, and you had this Br2, an Fe, Br3. What would that give you? Bromination.
Bromination.
And this is what would happen. Okay? Yes? You're going to have all of those on the test, and then you're going to have this good stuff, which is what she wanted to know. That is the what if. So let's say you already have this on the ring, and you try to do a nitration. And what would happen? So the CH3 would not be disconnected. These are conditions. Here's a benzene ring, yes? And here are conditions for nitration.
Nitration.
You are going to put an NO2 somewhere because this is nitration. Where is the NO2 going to go? Well,
It's gonna go opposite of
the NO2 is going to go depending on what type of director is already attached to the ring. So we are going to call these directors, and the directors are going to direct where the next electrophilic aromatic substitution will go. Yes? Hello? That's what you wanted to know? What if one group was already there?
Does that
So-
have anything to do with like deactivators and activators?
Yes. So you can have ortho para directors, and you can have meta directors. I'm dyslexic, okay? It's supposed to say directors, but it doesn't. It says that. I'm not gonna erase it, okay? I did it twice. I did it up there, I did it down here. I'm gonna leave it. So ortho para directors are activators. And meta directors are, of course, if one is activated, the other one has to be deactivated. How do you remember that? Because oxidation takes place where?
where you have less than.
Anode or cathode?
Oh my goodness.
You know, it's my pride for you guys to know stuff, you know. It is my pride for you guys to do well in your future. But I explained the stuff in 1046 and I thought I did it well, and now I'm finding out that no, I did not. Oxidation takes place at the anode, yes?
Yes.
Because vowels go together and consonants go together, yes? So oxidation takes place, of course it's not oxidation. Ortho para directors are activators. Meta are deactivators. You can do whatever you want with that information. Okay? So these groups that are activators, they are ortho para directors, and what type of groups are these? What type of groups are these? Electron withdrawing or electron releasing?
Activators and the deactivators.
Okay, look, I'm going to say it again. These groups are electron donating or electron releasing?
Releasing is donating.
Releasing is donating, outstanding. Releasing is donating, yes?
Yes.
Very good. So what type of groups are they?
Releasing or donating.
Releasing and donating is the same. These are electron donating, right? And these are electron withdrawing. I could make a mistake, right? I mean, you memorize this stuff, it is possible you forget, right? because you just don't know anything, right? You just forget it. So we're going to illustrate why this is by doing what? Mechanism. Very nice. That way, you only have to remember the mechanism. Which is what Sophia likes. Yes, Sophia?
Yes.
She wants it. So let's say we are going to have this group on it. Yes? And we are going to do an electrophilic aromatic substitution of what kind? What would you like? You want bromination? Okay, where is the bromine going to go? We talked about ipso, ortho, para, and meta, yes? Now, where is the bromination going to go here? You already have a group. This group is what? Electron donating, electron releasing.
Donating.
What's the same?
Same thing.
Releasing.
I prefer donating.
Electron withdrawing. Is it electron withdrawing?
No.
It's not electron withdrawing, yes? It's not. Okay, whatever it is. You are going to have, let's do the mechanism for this. Which one is the electrophile? Excuse me?
Ammonium ion.
The who?
Yeah, plus.
I have tried not to say bromonium ion, yes? I have tried. It is bromonium ion, but I don't want you to relate the bromonium ion to the bromonium ion for bromination of this alkene, right? Because I don't want you to relate this to the triple. Okay, to the, all right. Br plus, yes? Br plus, yes or no? Let's do it like this. So it gets attacked from this side. Okay? This is not what happens, yes? It is, this is why I put this here. What is this attached to right now? It is attached to the other bromine with the iron, blah, blah, blah. So I wanted to make things simple. So the double bond is going to attack it. Which double bond? This one or this one? This one?
Yeah.
Or this one? Or this one? Look,
It doesn't matter.
we can decide, yes? It doesn't matter. But let's say that we are going to do here, let's do ortho attack, since you can decide. And let's also do a para attack, since you can decide. Since you can decide, let's also do a meta attack. Do you want to do an ipso attack?
No.
No, not really. Let's skip that.
Why not?
Okay? So, this attack that we're going to do is going to be,
Ortho.
I am going to put the electrophile in what position? In the
Yeah,
ortho
ortho
position.
position.
Now, what ortho positions does this have? There's one there, and
Two.
then there's another here.
Yeah.
Doesn't matter where you put it. I am going to put it on this side, okay? Because on this side, it will be more problematic for you, okay? So, this is what is going to happen. That's an ortho position. This double bond is going to attack the bromine. Yes or no? And what happens? Tell me what happens. Hurry up, we don't have all day. Excuse me? It makes a bond.
Bond. Yeah.
Yes? Single bond to the bromine. Where is it going to be?
Right there.
Ortho, because we said it was going to
It's
be
an
an ortho
ortho
attack.
attack. Yeah.
Now this had a hydrogen here from before, yes or no? It had a hydrogen. There it is. This also had a hydrogen, yes? And there it is. There's hydrogens all over the place, okay? I am not going to put the hydrogen anymore after this event. Now this made a bond here. The electron pair from this double bond was used to make this bond. Now this carbon had a hydrogen, another bond, and the pi bond.
Yeah.
Now it doesn't have it.
No.
What charge is it?
Positive.
Positive. Outstanding. There you go. Amazing, huh? Of course, this is resonance
Stabilized.
so this has resonance structures that go with it.
Uh-huh.
And one of the resonance structures is what happens, double bond from here
Right.
makes a
The
double
bond
bond
and then that
there.
positive charge goes.
And here's a CH3. And here's the electrophile, which was
BR.
bromine,
Uh-huh.
the hydrogen here, hydrogen there. And now the positive is
Right there, yeah.
1, 2, 3, yes? It is 1, 2, 3. It could never be here.
No.
Never be here. Okay? Never. Because you would put these two electron pairs here. And now this will be satisfied. This always is satisfied, just
Yeah.
like a girl. And then that one is not satisfied.
Right.
All right. And does that have another resonance structure to it? Yes.
Yes.
Of course it does. And it's the one in which this goes like that.
And then that one will be positive.
And the bromine is still there
Uh-huh.
with the hydrogen.
Yeah.
And now there is a double bond here
Uh-huh.
with the hydrogen that was there from before. Now there is a double
Double
bond
bond.
here,
And
right?
the positive on
Double
that
bond
side.
here. And now the positive went. 1, 2, 3. Now the positive is there. My question is, which of those is the most
Most
stable
stable?
one?
The last one.
Well, the BR and
Because
This
it's
is the last
tertiary.
one. This is
Yeah.
the most stable.
Yeah.
This is
Tertiary
tertiary. Not
carbocation.
only tertiary, it is also,
Residence.
it is resonance stabilized. It is tertiary. What else is it? It is also a lipid. Okay? Very good. It is also a lipid. So this positive charge is distributed among all of these carbons, yes?
Yes.
By resonance. Okay? That was what attack?
Ortho.
Let's do para attack. Okay? You want that?
Yes.
Let's do para attack. Let's leave the double bonds where they were before. What time is it? You guys?
it's 10:45.
Until what time is this class?
11:30.
11:30?
11:45.
You guys want an exam next week on everything we've done so far? What do you think?
Yeah, next week.
Next week, Tuesday.
You guys, I mean,
Yeah, because
kind of a democracy type of thing, when would you like it?
With another chapter.
you don't want to be.
You want another chapter?
No,
Okay.
no,
I'm just trying to figure out.
Yeah, me too.
That was a question, was not another?
Okay, why don't we decide on Wednesday, how about that?
Whatever you want.
Because you guys need class.
Wednesday? Thursday?
Oh, we're not meeting on Wednesday?
No.
What makes you think I can't decide by Wednesday? All right, look here. Why did I choose this double bond?
As a para.
I mean,
Para position.
this is para,
Yeah.
and this is
Para.
meta.
Meta.
The para attack will put this group where? On the para position.
Yeah.
So I am going to say, I did do it from the double bond, yes? I did not start here.
Right.
You do not start here.
No.
If the book started here, it did it wrong, okay? And I don't care who wrote it. So I am going to put it here, yes? You have the CH3 here from before. This is the new incoming group, which is
BR.
Br. And there is a hydrogen here, yes or no?
Yes.
And what else? Double bond here,
Uh-huh.
and double bond here.
Yes.
And the plus
Positive.
is
Yeah.
there. It had a hydrogen from before, its hydrogen's still there. And now what's gonna happen? You are going to draw resonance
The
structures for
structures.
this. So I am going to make a double bond there. So the resonance structure is going to look like this. Now the double bond is here, incoming group is here.
And the positive is on top.
Double bond here, hydrogen here. Now the positive is
Positive
where?
right there. Yeah.
Positive is there. And you have yet another structure in
Mhm.
which this double bond will go
There.
there.
Uh-huh.
And now we have double bond here, double bond there, H, and BR, and H here. And where's the plus now?
Right by the BR on top of the, yeah, right there.
There's a plus there now. Okay? Which is the more stable carbocation so far?
The second one,
We're not
the
done
middle
with this
one.
mechanism yet.
No, so far is the middle one though.
So this is the most stable one.
Yeah.
It is tertiary.
Tertiary.
Is it the same stability as this one?
No,
It is the
yes,
same
yes,
stability,
because
right?
it's both a lily.
Tertiary, right?
Yeah.
Both tertiary, allylic, whatever it is. Let's do a meta attack.
Why is it the second?
What happened?
Why is it the second?
Why is it the second one?
Most stable.
Because it's tertiary, man. This one is the most stable because it's tertiary. It is the second one, and this was here the third, because we started on the other side of this thing. So we needed to get to here, which took 3 steps. Here we started here, so that was the second step. It doesn't matter. You're always going to have this one, and you're always going to have this one. Whether you start, whether it's the first structure, the second, or the third. Okay? Now, meta attack. Where's the meta attack at? Maria, where's the meta attack?
It's on the side.
Huh?
Power.
Which side?
Side. Both sides. Both sides. There's two
It could be
sides.
two.
Either side.
Meta.
I don't know why you hate that. I haven't done anything to you. So now the bromine is gonna be attacked. On which side?
On the
Meta.
meta side, yeah.
It's still from this double bond, yes?
Uh-huh. Yep.
Can it also be from the bottom?
From this one?
Yeah.
Yeah, it could also be from here. It could also be from here. It has meta is this position and
And
Yeah.
that
this
position.
position.
Yeah.
So if you attack it from here, you will place the
BR
incoming
right
group
there.
here.
Yeah.
If you attack it from here,
BR
the
goes
incoming
there.
group will be placed here.
Uh-huh.
So it doesn't really matter where you put it. Okay? What matters is
You
that
draw
when
the
you put the new group is going to be in what position?
meta.
In the meta position. I am going to put it here is the meta position. Yes or no?
Yes.
And now you're going to have a double bond here, a double bond there, and the positive charge is going to be
Right.
here. Yes or no?
Yes.
Okay? There is a hydrogen here. There is another hydrogen there. Now, by resonance, what's going to happen is double bond is going to go there,
Uh-huh.
and the positive charge is going to go to what carbon?
No. We're gonna go to the one next to that.
1,
2,
2,
3,
3.
right there. Yeah.
It's going to go here. Okay? By resonance, what's going to happen is another resonance structure. Where is the carbocation going to go now?
On the bottom. On the bottom of it.
Carbocation is going to go here.
Uh-huh.
Of these carbocations, is there one that is more stable
No.
than any of the others?
No.
No.
They're all secondary.
There is not one that is more stable than any of the other. What that means is that none of these carbocations are stabilized by the group that is there.
Oh.
So a meta attack
Won't happen?
is not favored
Okay.
for this type of group. Which attack is favored?
Power.
This attack is
Ortho.
favored. The ortho and the pair are what type of attack? They're the same. Yes?
Okay, yeah,
This
because
is
they
why
both
the
have
ortho
tertiary.
always goes with the pair, and the meta is all by itself.
Oh.
Because meta does not give you carbocation ever on this carbocation. It does not stabilize it.
Nice.
So these type of groups are what type of groups?
Ortho.
Electrons what?
Don't.
electron donating or electron releasing groups are ortho
Ortho or para. Okay.
And what do they do to the benzene ring? Do they activate it or deactivate it?
Activated. They activated.
Activate it. Why do they activate it?
Because it makes
donating
us electrons.
This needs to do what? Use electrons to attack, yes? So if you give it more electrons, then this ring has more electrons to attack. Okay, make sense?
Yes.
I think that's what it is, I'm not sure. Why don't you read the book, okay? What else? What else, my friends? So, things that are electron donating are those that have, is this electron donating? Hello? Is electron donating? How about this?
CF3 withdrawn. That's withdrawing because of fluorine. It's withdrawing.
Electron
Withdrawing. Yeah.
Electron withdrawing. So if it is electron withdrawing, group electronegative element next to it, this will be ortho-pair or
Meta.
meta-director.
Meta. That's meta.
Meta-director. Is it going to be an activator or deactivator?
Deactivator.
Deactivator. It's going to slow down the reaction, yes?
Yes.
It's going to speed it up, it's going to slow it down. How about this? Ortho-pair or meta-director?
Meta.
Meta-director, because this is electron
Electron withdrawing. Meta.
What is that going to be? It's
Meta.
going to be meta-director.
Yeah.
What is that going to be?
It could be both.
That's an S.
No, this is an ether.
Oh,
Ether.
no, wait. It could be. It's
Because all is
donating.
connected to the
It's
benzene.
electron donating.
It's gonna be ortho.
It could be either one.
So it's ortho and para. Yeah, ortho and para.
This is gonna give it to.
It's ortho and para.
Hello?
Ortho and para.
I explained last time, okay? That
Because
if
of
the
resonance,
element attached to the ring has electrons on it, right here, it will be ortho pair.
Yeah.
What is that going to do to the intermediate? The intermediate is gonna end up being this, yes or no? Yes or no?
Yeah.
Yes.
Well, not completely
Not
this,
completely
yes, let's
that.
say that. That's going to be the intermediate. You see it here or no? For ortho pair. Hello? So, if it is either in this position or in that position, it will make this. And this is stabilized by this. How?
Resonance.
Well,
The resonance
it will
is
say,
gonna be
okay,
down here.
we go in there and it will make that double bond.
Right.
It will stabilize that positive charge.
Right.
Okay? How about this? Ortho para or meta?
It's,
Meta.
meta.
Collagen.
Well, the CL, so it's gonna do the same thing, so it's para. It's para.
It's
I
para.
mean, I did say that if it
Ortho
has
para
electrons on it,
It's
it will
withdrawing.
be
Para.
Ortho
para.
para. Yeah.
Collagen.
Huh?
Well,
What do you mean it's a halogen? Look here.
Oh. Never mind.
Now, is it going to donate it?
Collagen.
it's gonna.
No.
Hello?
No.
Is it going to form this thing here?
No.
No, it
No,
doesn't
it
want to
doesn't.
form
No.
that.
No.
It doesn't want to form that. But it does have electrons, right?
Yes.
It does have electrons to give. So this would be ortho-para director. Okay?
That was nice.
Should we do all three attacks again for meta directors?
Yeah, we can.
What do you think, Sophia?
No. So we got it.
You want it? All right, you got it. Since you asked, okay?
No, I didn't.
Yes, you did.
Wait, and I saw that, that's why I yelled out halogen. Don't halogens Isn't there an exception to halogens when it comes to activator, deactivator?
Yes, there is, but I'm not saying that, I'm saying ortho-para-director, yes or no?
Okay.
Ortho-para-director. Okay? They are deactivators. And the reason why they are deactivators is because electronegative, yes? So it is pulling electron density from here. So it's deactivating the ring. But so we are going to do another halogenation, yes? So why don't we just say electrophilic plus, yes? So I want you to do ortho attack. I want you to do para attack. And I want you to do meta attack. You try to do it by yourself. And if you can't do it, it's okay. Not everybody can pass the class, okay? Fact of life.
Oh, excuse me.
Somebody's got a question. I don't know.
Guys, you did it?
Yeah.
You want to change where the double bonds are at, or that's okay? That's okay?
Yeah.
So here is, what position is this called?
Ipso.
Ipso. Things are compared to that position, okay? If I were drawing this, what position is Ipso to that? Which is the Ipso
Ipso
position?
position where the NO2 is.
NO2 is his Ipso position, and which was the ortho? That's ortho, this is meta, and that's para. Okay, so it doesn't matter how it's drawn, that is the reference, and the reference is called Ipso.
Okay.
Okay, so there you go. And when it does the attack, this is going to be ortho. So where am I going to place this? I'm going to place it in the
Ortho position.
ortho position. That's why this is called
Ortho attack.
By the way, how does that NO2 look like? Hello? Like this?
No, double bond.
Double bond to an oxygen?
Negative.
That has 4 bonds already.
Yeah.
So
Negative.
minus,
That's plus.
positive.
Yeah.
Okay? And I put it, where was it? Ortho. There it is. And where's the plus charge at? Where's the plus charge
On the
at?
bottom of that
On the
electric
bottom, what
file.
position is that?
Yeah.
Meta position.
Meta. Yeah, meta.
So it's gonna be here. And resonance structure, in which this goes like that. Kind of tired of drawing this. You are going to be Superman on that test when you draw these. Draw these in 2 minutes, max. Positive is there, double bond here, attack was ortho. There you go, another resonance structure, yes or no?
Yes.
In which? Is this what you did? I forgot to do the last part here, right? Didn't I? Yeah, we forgot to do the last part here, right? In order for us to develop the aromatic ring. Yes, again, that has to get, I did it the first day, yes, but I didn't do it from all of these. On the last step here, some type of base. Okay, the base could be Br minus during bromination, right? Because you had this, yes?
Right. Yeah.
One Br became Br plus one, the other one became
Br minus.
Br minus. So the Br minus pulls this one off,
Right.
and that goes like that,
Double
and
bond.
makes a double bond, okay?
Yeah.
So, where are we at? Here, electrophile. Yes or no?
Yeah.
And where's the positive charge right now?
Right there.
Here. How good is that? It's good? You like that? Really?
Is that?
No, because it got 2 positives.
Wow. In this case, you gotta draw the
Can it have 2 positives like that? That's not good.
because of this. Is it?
No, because it got 2 positives,
Are
right?
you kidding me? That is a positive here.
And a positive positive.
It's not good.
That's not good.
It's not good.
Yeah.
Is this nitrogen gonna make a double bond here?
No,
With what electrons? It doesn't have electrons to give.
but
I don't
it
see
can-
an electron pair. Do you see an electron pair in the nitrogen?
No,
No. They can't give it.
but it
If it were
can.
this, if it were that, it could give it
Yeah.
because it has electrons on the element here,
Uh-huh.
but it doesn't.
No.
It's not this one. This would be orthopair, but this is not orthopair because the orthopair attack will be destabilized with the neighboring positive charges, yes?
Right.
Hello? So the pair attack would be the same, yes? I'm not gonna draw it. Okay, let's draw the meta. Yes?
So where does it go from there?
Where does it go from there? Well, I mean, it doesn't want to go here, yes?
No?
With the two positive charges, so this mechanism is not the best
Oh,
one
okay.
for this.
All right.
So it does not want to do orthopara if it is electron withdrawing, yes? Because the carbocation formed from an orthopara attack is destabilized. Now that doesn't mean you don't get 1% or 2% or 3% of this. That means that this is not the major product, right? This is a
Right.
bad thing. So the same thing for for ortho attack. Do the meta, please. You do the meta. Maria, you still a vegetarian? Good. I was a vegetarian for a week and a half,
So depressed.
and I almost died.
How important?
I know. You mean me dying or that I stopped being a vegetarian?
The latter.
Vegetarian. I could die and it's not unfortunate. I got it.
Doesn't matter. Positive end up right there on the secondary. Which is better than
What next, guys?
So the meta attack.
Meta attack.
Yeah.
And meta attack would look like this. NO2.
Uh-huh.
Yes. Meta attack would look like I am going to put the group where? Here, yes? Whatever that group happens to be.
Uh-huh.
And the positive charge would go where?
Right above it.
Would go here.
Good.
Yes?
Yeah.
And double bond will go there.
Uh-huh.
The positive charge will go to this side, yes? Another resonance structure in which this goes here. And the positive charge would go where? Positive charge would go here,
Which is better.
okay? So what is the problem with this? The positive never has another positive here.
Uh-huh.
Because it never has a positive here, you can see the positive is either ortho to this,
Yeah.
ortho, or
Para.
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 It is never here, so that resonance structure is
It's
better.
better. The meta is better.
Because of this, electron withdrawing groups are what type of directors? Meta directors, okay?
Which, out of one of the three, you said which one was better?
Meta.
Meta. No, wait, I'm saying like on the bottom, you were saying that.
None of those resonance structure, I mean, none of them are better than the other. They're all the same. It's just none of them are as bad as this, yes?
Right.
This is bad. This, it's not that bad, so I guess it's good, yes? But it's not good either, but, okay.
It's the lesser evil.
You got it? No? Whatever. What type of group is that? Ortho pair or meta?
Ortho parent.
Ortho pair, because?
Because it's withdrawing.
Because, did you say 3 electrons?
I said those little free electrons.
Oh, 3. Oh, yeah, 3. Yeah, because of these free electrons, like free-range chickens, okay? They're not really free. So, yes, because it has electron pairs right here. Now, which one do you think will have a larger effect? This group or that group?
The one to the left?
Larger effect. Which one would be a better donor?
That,
The one with the two lights.
This would be a better donor.
Why?
Okay?
That's two.
Because this one is getting a little bit of that oxygen is being withdrawn by this
Because
carbon.
inductive.
So this is more of an activator than this
That one.
is.
Okay.
So this is a strong activator, while this is a moderate activator. Like a deactivator would be Cl. Is that weak? This is weaker than that. Okay. Here's homework for you. I want you to summarize all the reactions for electrophilic aromatic substitution chapter. For the chapter, not only electrophilic aromatic substitution, all of the reactions. Reactions only, not mechanisms, yes? How do you do this? Hello? How do you do that? What is it? Friedel-Crafts alkylation, that's right. I get this from this reaction. Benzene ring, yes? With? Hello? How many carbons?
2.
2 carbons. 1, 2 carbons, and what here? And H?
No.
No, F80.
H2SO4.
What do you think?
H2SO4.
Guys, what is the Lewis acid used for? Because look,
AlCl3.
Karen is not
AlCl3.
here, okay? But the message to her is, I am maliciously hiding this from you, okay? Because I want you to get this wrong on the test, okay? I'm going to give you something called Friedel-Crafts alkylation. And the Lewis acid for this
AlCl3.
is Al
Br3.
Br3, okay? The Lewis acid is not Fe. FeBr3 or FeCl3 is for bromination or chlorination. For Friedel-Crafts alkylation or acylation, that's what you get. Aluminum.
Why?
Because it's stronger Lewis acid, okay? And that would give you this. Yes or no? Huh? Let's say you have this. What's that called? Toyuyin, yes? Toyuyin?
Yeah. Toyin.
Huh? Toluene. It's not toluene. It's toluene. All right. If I treat this with
NBS.
NBS,
Yeah.
which is N-bromosuccinimide. This is radical conditions.
Uh-huh.
The radical conditions, what would you get? You
BR.
get
BR.
radical bromination.
Yeah.
You get a BR. You'd get a BR in the, what's this position called?
No.
Ipso.
So no, that's ortho.
What? Ortho. Benzene. Holy moly.
Well,
Why is it ipso? Should they have the
it's not.
position?
It's not ortho either.
It's not ortho. Ipso is here. Ortho is here. It's not bromination of the ring, okay? This is not called electrophilic aromatic substitution. This is radical bromination, and it occurs at the benzylic position. Okay?
Why is that a
And-
benzylic position?
Because I explained to you in 1040 organic 1, okay? Allylic bromination, yes?
Yeah.
And, okay, put it this way. Where it doesn't matter what you have, let's say you have this.
What the hell is going on?
Bromination will be in what position? In this position. It will always be allylic, yes?
Yeah.
This is not allylic here, but it is a carbonyl. You have this one, okay? It takes place here. Let's say I had this. Let's say this an ethyl, and this is an ethyl, and this is, let's say CH3. And I treated with this, with NBS. And you don't know, you've never seen this reaction before, but you know that bromination, this is allylic bromination, yes? Hello?
Yes.
Or it is benzylic, or it is next to whatever double bond you have. So what is going to happen here? You are going to put a
Replace
bromine
the
here.
C. Yeah.
Yes? Yes or no?
Uh-huh.
So if you treat with this NBS, you are going to put a bromine where?
Right there.
In this
place
position.
Yeah.
If it had another
Benzylic.
carbon, where would the bromine go?
In the benzylic.
Hello?
It would go at the end. It would go at the
Yeah,
end.
the end.
At the end.
At the end?
Wait.
This here, radical here? No, this
No, it's-
radical is
it's-
primary.
right, it's gotta be
It's not
tertiary.
good. This is a radical, this is secondary, and it is? Well, it's not called allylic. If it were this, it wouldn't be called allylic. But this is called benzylic. Benzylic is like allylic for an aromatic ring. So the bromination would go there. That's one bromination. If you use excess of this, you'll have one bromination, and then another bromination, and another bromination. So with one bromination, you would get
BR.
you get a BR here,
Uh-huh.
H and H, yes? And if you use excess, as excess NBS, what would you do? What would you get?
It's BR.
Huh?
CBR3.
Okay. Now, if you were to treat this with, let's say, sodium
NaOH.
hydroxide,
Yeah.
okay? If you were to treat that with sodium hydroxide, the OH will attack, yeah, the sodium does nothing. The OH would attack that in what type of reaction? It's a nucleophilic
Philic.
reaction,
Yeah,
SN2,
SN2.
okay, SN2. Or it could be
SN1.
SN1, but it
Yeah.
doesn't matter what it is.
No.
It doesn't matter.
Because it's going to have the
Still
same
a
product.
substitution. We are going to get this thing. And I think I talked about this last
Yeah.
class, didn't I?
Mm-hmm.
Hello?
Yeah, it was last class.
You get this. If it is SN2, it is inversion of configuration. If it is SN1, it is racemic.
Racemic.
If it has stereochemistry, yes?
Yes. So you could do like
Or you can have a
PCC.
mixture of both.
You could do PCC.
And you can oxidize that with PCC. Let's say you have this. And you treat this with potassium permanganate.
Uh-huh.
What would it do?
Give you a carboxylic acid.
Give you a carboxylic acid. And let's say you treated this with potassium permanganate. What would you get?
Carboxylic acid.
And let's say A what? PBS? You mean the
The kids
PBS
channel?
for kids? Yeah, they play little cartoons. Yeah, they play cartoons. I see that channel, I love it.
Me too.
It's great, right?
That's the only thing I let my kids watch.
Yeah.
PBS Kids.
My daughter watches the Disney Channel.
Oh, I hate that.
Liv and Maddie with boyfriends and all this
Oh,
stuff.
no, I
She's
hate
8
that.
years old. They're gonna try to kiss. I cover her eyes. I don't even think about it. Don't even dream about
Ah, yep. My daughter's the same thing, man. I hate when she watched that Disney damn channel.
this. All right. What else? We have this. We can make this. What type of reaction would that be? Oxidation or reduction?
Reduction.
Reduction. And the reduction will happen, let's say, with zinc and HCl. You seen that one before? Hello?
No.
You've never seen it?
Yeah. With,
No? We did not do it in 1046?
I mean,
Definitely not in 1046, yes? 1025?
maybe.
You did not have me for 1025. Okay, that's where I did it. All right. So, what else? Let's say, we have this. And we are going to make this business. It's what type of reaction is that? Reduction still. Okay, we can do this reduction with something called zinc amalgam. The reason why I gave them both to you like this is so you can relate them. They're both what type of reactions?
Reduction.
Reductions with the same thing, zinc and HCl.
HCl.
Difference is, this one is a little bit worse to reduce, so you need this mercury. thing.
Yeah.
Okay. What else? We can do. Oh, we can't do it now, huh? What are we going to do for homework for Wednesday? This for Wednesday.
Summary of all the
Don't try me.
reactions.
Yeah, don't try. Everybody is going to do what for Wednesday?
Homework.
You are going to
Summarize all the reactions.
for this. I want you to look for this up on top of all of that stuff. It's only like half an hour to do all of this. So don't tell me you do not have time. You hear Louis? Louis Lamiste. You're not Louis? What are you?
Chase.
Chase? What are you chasing? Dude, it's called nucleophilic aromatic substitution. Find out if this reaction takes place. If this were benzylic, would it take place? If it were benzylic, it would take place. I already showed you, yes? But let's say you have this. Would this OH attack this? And then would this leave?
Yes.
It would? I want you to find out if it would or not. And under what conditions it would do it. Okay? And this is so, you look for this. We had electrophilic, yes? And this is called nucleophilic. What?
Aromatic substitution.
Aromatic substitution. And do not ask Mitch. Huh? Mitch is that guy in the back. And he is the tutor for this class, right?
Yep.
Right, Mitch? So don't be training him. You guys are girls mainly. They're leeches, right? Sucking on everybody's blood.
That's in the book.
I think it's in the book. Either this one or the other.
Yeah, the other one.
Okay, guys, congratulations. Another day.